All right, so last time we were looking at, we gave a preview of error handling, and today we're going to give a more formal introduction to error handling. But basically, we want to do error handling because programs always have the potential for errors. Now, when I say errors, I don't mean errors in the logic, like the errors that you would have, like a bug or something like that, or a syntax error because you didn't follow the rules of the language, right? These are errors that can occur when a user is interacting with a program. Some errors can be unexpected. For example, you lose a network connection if you're connecting to a server, or somebody enters in a wrong password or something like that. Ultimately, you can anticipate some of those errors and protect yourself against them, though, right? And the way that you do that is you write code to test for these conditions. You're going to divide by 0. You're going to take a square root of a negative value. There's a null pointer, et cetera, right? And then you handle them somehow. You choose not to do those dangerous things, or you have some sort of a contingency where you do something else, right? Sometimes errors can be fatal, though, right? For example, the network is lost entirely, and you're trying to process something on the server. At that point, there's really nothing that you can do to recover, and maybe it's appropriate for you to end the program and just quit, right? Because there's no way for the program to recover. In C, our general strategy is going to be what's called defensive programming. Now, defensive programming simply means that we are going to, let me check the audio. Yep. It simply means that we're going to check for these error conditions. And if we're about to do something illegal, like, say, dividing by 0, then we don't do that thing, and instead we do something else. All right? This is what I call the looking before you leap strategy, right? We're going to look to see, are we about to do something dangerous? If we're okay, then it's okay to take another step. If we're not okay, that means that we're about to fall off the edge of a cliff. We don't do that thing. We do something else. As far as code is concerned, it means that you have an if condition. You check for these bad conditions, and you don't do the potentially dangerous operation. Instead, for our case, we're going to actually return an error code, right? So, inside of a function, to do error handling, what you do is that's the first thing you do. If there are error conditions, you immediately return to the calling function. Right? You don't do anything else because everything that you do might cause a fatal error, right? Also, you communicate to the calling function that an error occurred. That's what we were doing yesterday. Now that we're passing stuff by reference, and then our return values are going to be passed by reference variables, then that frees up the return type. Instead of a void function, we created an int function that returned an integer variable that communicated the type of error back to the calling function, right? And that's what we're going to do. By convention, remember, 0 is no error. You're basically asking the question, was there an error, true or false? False. The only thing that is false is 0, so that's going to be our error code for no error. Otherwise, 1, 2, 3, 4, whatever, indicate errors of various types. You don't generally use doubles to do this. That's kind of weird because doubles are inexact. And also, you don't use negative values because generally this is going to be an unsigned integer in a lot of ways. What you do not do, right? So bad error handling. You do not print anything in the error message, right? Print anything in the function, in the function, right? In other words, we're not going to print any error messages. Remember, the whole reason that you write programs is you automate stuff, right? If you have a bunch of error messages being printed out to the screen, that is assuming that somebody is sitting there 24/7 watching the screen, waiting for something to happen, and then jumping into action when they see that error message, right? That's not the way that we do things. We do log messages. So, for example, major programs will have system logs, and they'll output everything from somebody tried to log in and there was failure at 4 p.m. today, right? Well, it was just a bad password. That's not an error in the program. That's an error on the user. Somebody tried to access this web page, but the web server failed to do it. Okay, that's something I'm interested in. Maybe I need to go back and find out what happened at 1:30 yesterday. You can see this stuff in action. We've got plenty of time today, so I'm going to go ahead and show it to you. You can see this stuff in action on an actual web server. Let's see. Nope, that's not the web server I want to go to. So SSH CSE. This is another one that you don't have access to. Sorry, but it's the CSE server. And let's see. Tail is a utility that allows you to look at the contents of a file, but only if they're updated. So I'm going to go ahead and tail the what is it? Apache logs. There we go. Apache logs. Apache is our web server. It's a standard web server. And let's go ahead and look at the access log. There we go. So you'll see this get updated as more and more people are hitting our web pages or whatever for the School of Computing. For example, somebody at those IP addresses is probably pinging us. It's probably a bot or some sort. And they're getting a 302 error, an HTTP 302 error. But this allows you, oh, look, somebody tried to access my book. Good job. I don't know where you are, but you are from, there's your IP address. We can look you up and see at least where you are in the, I don't know, we could do that. So, IP locator. This is all stuff that you can do, and it's a nice little fun thing that you can look up a geolocation. We'll just get a general area here. Okay, so somebody in Japan is probably a bot, right? But otherwise, somebody did try to access my book right there. Great, and they got a 1. They were trying to access it through HTTP 1.1. 200, they got an OK error. It's not an error. It's that 200 code is an HTTP code that says they successfully got that resource. And they're also trying to access my Git tutorial. It's probably just some scraper that is accessing absolutely everything and then doing something with it. Who knows what they're doing with it? But in any case, we've got, yep, there's a bot. But you can take a look at system logs later on. Nobody is sitting here like I'm doing or like we're doing right now saying, okay, I'm going to watch this, and then when something bad happens, I'm going to spring into action. No. Instead, when something bad happens, they notify Scott down in the basement, and Scott goes back to the system logs. When was this? 1:30 yesterday. Starts looking at all the system logs for 1:30 yesterday. That allows him to only focus on that which matters. Ultimately, though, we're not putting them to the standard output because nobody is sitting there watching them. Right? So you don't print an error message. The second thing that you don't do is you don't quit on the program. Right? This takes any design decisions away from the programmer, right, or the user of your functions or library. Imagine if square root, you called it on -1. Imagine that just quit the program on you. Right? Would you want that to happen? Probably not. So don't design functions that do that, because it takes the decision-making process away from the programmer, right? Or we call him the user. Even though it's not the end user, we are the users, right? The only time that you should ever exit, like we've been doing up to this point, is in the main. That is okay, right? That's because, well, you didn't give me enough inputs. I can't possibly continue with this program. We're just going to quit, right? But otherwise, if you call a function, it should communicate, no, those are bad inputs back from that function. Then maybe we'll decide to quit, or maybe we'll decide something else. We'll go ahead and give it default values. Or like we did yesterday, if they gave us bad values, or on Wednesday, whenever it was, if they gave us bad values, what did they do? What did we do over here in the demo, right? Hey, that's a linear equation, but I'll go ahead and give you a solution for it anyway. And we did something else. If this function, compute roots, decided to exit on us, we couldn't have done that, right? And that would have been a bad design, or at least it would have been a very inflexible design, and I probably wouldn't have used that function. I would have written my own function to do it, and a better design function, a way of doing it, right? So those are the two things that you don't do. Make sure that when you're doing error handling, null pointer checks are always done first, right? Because you don't want, you want to check to see if it's negative, right? Well, I'll check to see if it's negative, then I'll check to see if it's null, right? No, if you check to see if it's negative and it's a null pointer exception, or a null pointer, then what happens? Bret Hart hits you up beside the head and says you can't dereference a null pointer. Null pointers are always the first things that you do. Failure to check them, again, remember Bret Hart, right? That's dereferencing a null pointer and just hit yourself upside the head and saying, I should be doing something else. Again, to reiterate, you do not print anything. You do not exit. You only communicate the error type and condition back to the calling function. And the way that we did that on Wednesday was through this error code, right? Where is it now? Here we go. we check to see if they were null. If so, we return this null pointer error. Do you remember what number we assigned that? Well, we just started with 1, 2, 3, and 4, right? Complex root error, divide by 0 error. We provided user-friendly or user-readable, at least, ways of describing these error codes, right? Now, what I'm going to do is I'm going to show you a little bit better way of doing this. What we were doing before was perfectly fine in a lot of respects, using a bunch of defines, okay? Here's an alternative way of doing it, and that's going to require a new concept called an enumerated type in C, right? So many pieces of data have a fixed number of limited possible values. For example, the days of the week, right? How many days are there in the week? 7, and they ain't making any more, right? Or months in the year. How many months there are there in the year? Months in the year? 12. And sometimes they make more, right? History, we used to only have 10 months, right? July and August got added. Why? Because of Julius and Augustus Caesar, respectively, right? So maybe sometime in the future we'll have more months or something like that. But it ain't changing anytime soon. And then finally, of course, error codes, right? So why do we call these things enumeration? Well, what's an enumeration in real life? It's just a list, right? I like cake, ice cream, soda, blah, blah, blah. These are the list of my favorite foods, whatever, right? And so you can, in C, you can define an enumerated type that has human-readable possible values for this. I'll just keep it over here. Let's go ahead and take a look at an example here, say for the days of the week, because it's short enough, all right? So the syntax for doing this, let me jump down here, there we go, is going to be type def, which is short for type definition. And what are we going to define? We're going to define an enumerated type. Enum is short for that. Okay. I'm going to jump down to the bottom here and give it a name, day of week, because that's what we're doing. That's what it's representing here. So at the very end of the closing curly bracket, we provide the name of the type. Okay. We're going to use that later on and actually create a type, not of integer or double or char, but of day of week. Right? Then we have a semicolon at the end, so notice that too. When does your week start? Okay, my week starts on Sunday too, right? My Strava app thinks it starts on Monday, so it always tacks on my Sunday run to the previous week, and I don't like it. But then we have Monday, right? Tuesday. In fact, while I'm writing these, do we know what the days of the week are named for? Sunday is pretty obvious. It's the big bright thing in the sky, right? Monday is also pretty obvious. It's the other bright thing in the sky, the moon, right? Tuesday, I think it's the Greek god Tyre, maybe Tyre's day, or maybe that's Norse. I don't know. Okay, it's Norse. Thank you. Yep, and also Wednesday is Odin's day. Odin, the Allfather in Norse mythology. Then Thursday is Thor, right? Friday is Freya, his wife, Odin's wife. Anybody know? Freya, I think. Saturday, there we go. Now we no longer have. Now we have Roman, Saturn, the Titan, right? Not a god, but a Titan, right? So that's what all of our days of the week are named for, right? It's a list. A list is delimited by commas. Now that last one is called the coding Oxford comma. You can go ahead and remove it. You can keep it if you want. Doesn't matter, right? The reason that you would want to retain it is if you've got more to add later on, you have to go back and add the comma, and you might have forgotten. So leave it, don't leave it, or leave it off. It's up to you, right? It's a style choice, okay? But otherwise, there are only 7 days of the week, and there they are. Now, later on in the program, someone is later on in the program, I can create another variable that is of type day of week, right? Today, and set it equal to Friday, right? That's because I've now defined my own type, my own user-defined type. Now, there's some limitations here, and gotchas and weird stuff that can happen. But I can create another one, day of week. Tomorrow is equal to Saturday. Right? Okay? And I can say if today is Saturday, then printf football, at least for the fall. Right, there we go. There we go. Yay. Right. So you can treat it like any other variable, like mostly like an integer variable, because under the hood, that's what it is. It's just an integer. And it comes with the same pitfalls. So careful. You can also do something like this. Today is equal to Saturday. That's the last day of the week, right? What if I said today plus equals 1? What day is it now? Now, in real life, it would be Sunday, but that is not how it happens now. So what happens is that each one of these is assigned an integer variable. Sunday is assigned 0. Monday, because it was the first one in the list. Monday is assigned 1, 2, 3, 4, 5, 6. Saturday is the 7th day, and therefore it is 6, because we started at 0. What value is this now? 7. Invalid. Right? The reason is because there really aren't enumerated types built into C. It's just syntactic sugar that allows you to make a human-readable list. At the end of the day, what's happening is that it's assigning a bunch of integer values to these, just like our defines did. Okay? So these are not actual types. C simply uses integer placeholders that are automatically assigned. 0 is, in this case, Sunday was 0 because we started out at Sunday. So if you'd answered differently and said, like the Strava app, that Monday comes first, Monday would have been 0, and Sunday would have been 6 at the end. Right? As a consequence, you can mistreat them as integers, but don't do this. Don't do this. Right? Don't paint yourself into a corner like this. Right? If you're going to use enumerated types, then great, use them, but use them only as enumerated types. All right? It's best practice to just use them properly. Observations on style. Right? Use upper camel under underscore casing for values. Now, why would you want to use that? Because it's the same thing as a constant, right? Sunday is Sunday, and it's not changing, right? Monday is Monday, and it's not changing. Use upper camel casing for name types. Name types. That is day of week, error code, etc. Right? That convention is because that's more modern convention. It means that it's not a variable, right? If I were to create a variable number of students, I would use lower camel casing. Upper camel casing tells me, oh, that's the type. Okay, just be consistent about it. Usually, you only do one item per line, right? Because it looks nice, right? And it's separated by commas, and all of them are inside of the curly brackets. At the end, you provide the name and a semicolon. Right? If it doesn't have a semicolon, then it's not the end of the declaration. Right? Generally, you declare enums in a header file. Right? So let's go back to our demonstration from Wednesday, and let's change all of those defines into an enumerated type. Okay? So I'll go ahead and retain this eventually when I post the code so that you have it, but that's the way that we did it before. Generally don't do that. Get rid of your cruft. Don't leave dead code. I'm leaving this so that you can see it when I actually post the code. Instead, we're going to do an enumerated type. Type definition, and it's an enumerated type, opening, closing curly brackets. And what should we call this thing? Error? Well, we could call it error, but then a lot of people are using error codes, right? Error code, that's even better. It's even better to make it so that it ties it to your library. Util error code, that's good enough. Because our library is called util, right? Because what if I bring another library that also has error codes defined, right? So I'm going to tie it to my library here, okay? Now I'm going to go ahead and grab these and put them into a list. But be careful. If I do this blindly, what value does null pointer error have right now? 0. Right? So we should have something before this that takes on the value of 0. No error. All right, there we go. I like that. or error-free or something like that. No error is what I like. Right? So let's come back over here, and we've already done it. The only thing that I'm going to change now is this 0. I'm going to change it to no error. Right? Okay. Otherwise, it works just as before. Right? Now, the advantage. Now, why would you do one way or the other? There's internal debate among C programmers that says you should do type defs. You should do an enumerated type, or you should do the other one, 6 of one, half a dozen of the other. The one argument that I've seen that would make me lean towards enumerated types is if you're running it through a debugger, then you don't lose this information. If you run it through a debugger and you use the defines, you end up losing everything, and it only becomes 1. It becomes the mysterious magic numbers again. That's a good enough, in my book, argument that you should use enumerated types for this. All right, we'll use a debugger later on, and we might see what happens there. But basically, remember that the preprocessor goes through, and every time it sees null pointer error, it erases it and places a 1 there, and that's why you lose information about it when you get to the debugging phase. Okay. One more thing that we can do here now, instead of returning an integer, it returns a util error code. Right? So let me change that here, and let me change that up here. And also let me change it in my demo up here. I mean, it's still going to compile. GCC C utils.c, always with the wall flag there. Perfectly fine. GCC utils.o and the demo, and we're linking the math library if we need it. Right? It will complain about some. What are you complaining about? Oh yeah, 42. Okay, let's fix that. Should be ampersand R1, right? Otherwise it will crash. There we go. And run it again, and we get the same roots as before. In other words, it doesn't matter if I make this into an integer or into utils error code, because at the end of the day in C, there really is no such thing as an enumerated type. It's just doing syntactic sugar, and behind the scenes it's an integer. But it's best practice to still do this. All right? Okay. All right. So, let's see. Okay, good. So, as another part of this, let me show you how C does its own error handling. Now, this isn't something that you're going to use directly, but it's something that you should be aware of. Okay. Internally, C actually defines 3 different types of errors. Only 3 different types of errors. They're all defined in this error no library. All right. All right. And I should quit that by now. There we go. If it was bothering anybody in the background there, sorry. Anyway, there's an error no library here. The C standard actually only defines 3 different errors. EDOM is an error in the domain of a function. In other words, the input. If you remember back to your math classes, when you've got a function that maps a set of numbers to another set of numbers, what do we call that first set? The domain. What do we call the second set of things that it gets mapped to? That's the range, right? Or the codomain. So an E-range error indicates an error in the range of a function. EIL, illegal SEQ, that's an illegal byte sequence. I've never actually seen that in practice. But if something fundamentally screws up at the hardware level, that could happen. All right. Let me show you a demo here. CSC 155E, programs, and then error handling. All right, let's look at this error demo here. Here's how you could use the library. Not that you'll need to use it in this class at all, but here's how you use it. So I've created a bunch of variables here, and we'll come back to those. But otherwise, I call square root on b, which is 2. The square root of 2 is perfectly fine. So what we'll do is we'll print out the result, and we'll also print out this thing called error no. This is a global variable. We haven't talked about globals because globals are evil and you should not use them. They are evil because if you are in a multi-threaded programming environment, you have multiple threads or multiple programs trying to access the same variable. Now you've got synchronization problems and everybody's stepping on everybody's toes. Not only that, but globals, if anything can see it and change it, that means you have to test for the eventuality that anything will change it. Total chaos. But in any case, that's how C does it for error handling. That if you ever call a library function and it results in an error, there's this value, which is an integer, that gets set to one of these values. So in this case, there should not be any error because square root of 2 is well defined, 1.41 something something something, right? So what value would error no have here? 0, because 0 is no error. Now I call square root on -1, right? What kind of an error would that be? Is the function defined over here in the domain for -1? Nope. So what ends up happening is the result is not a number and an E-domain error, E-DOM error. And we can print that out, okay? And then I've got a bunch of stuff that if it was an E-DOM error, I print that out, E-range or illegal byte sequence or it was some other error, right? Error messages can also be accessed. If you call this function str error, str is short for string, it translates this error number into an error message that then can be printed out. It's not going to be that helpful, by the way, right? All right, what I'm going to call x is equal to log of c. Now, if you remember up here, what was c? 0. So what's the log of 0? If I were to graph it, what would it look like? I'm going to approach 0 from above. It goes down, 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 down. Eventually, when you get to 0, you can never get to 0. But what ends up happening? Negative infinity, right? So we're going to end up with probably -in for not a number, something here. But ultimately, it's going to end up being an E-range error because is negative infinity in the range of numbers that we can map to? No, right? So we'll get a message there as well. I already compiled this, I think. Come on. All right, A dot out. Let's see it run. There's that original call with the square root of 2. There's no error, 0. When we called square root of -1, it was not a number, and there's an error code of 33, which corresponds to this E-DOM error, numerical argument out of domain. We called log of 0, which is -inf, and a error type of 34, which is an E-range error, numerical result out of range. All right? C only defines these 3, right? Generally, you're not going to use this library directly. Generally, you're going to make your own error codes because you're writing your own stuff. But there are other standards that define more than just these 3 errors. The main one is called POSIX, or Portable Operating System Interface. And I'll give you a hint. There's only one operating system out there that does not do this standard, this POSIX standard. And it's owned by Microsoft. Windows does not conform to the POSIX standard for whatever reason, right? But otherwise, every other operating system out there, Linux, Unix, my Mac, which is BSD, right? They all conform to this POSIX standard. Portable Operating System Interface. They're trying to be portable across all these different devices. Now we can look it up. POSIX errorno.h source. Maybe that one's good. Yeah, here we go. So there are a lot more errors than just EDOM. There's our EDOM, which is defined by the standard. There's our E-range, that's defined by the standard. We can even look at illegal sequence. There we go. Invalid or incomplete multi-byte or wide character, whatever that means, right? But otherwise, there are lots more. There's about 100 others. For example, bad file descriptor. Oh, there we go. You're trying to write to a file, but your quota was exceeded because you only have 2 gigabytes or something quota. Then it would raise that kind of an error. The file exists, but you're trying to overwrite it. All right, there's an error, right? File is too large because there's a limit to the size of files on systems, right? So there are a whole bunch of errors like this, and if you were doing systems level programming, you would have this out on your desk at all times. Figure, okay, what could happen here? What could go wrong? I'm trying to open a file. Okay, well, look at all the file errors that could occur, and let's write some defensive code in the event that happens, right? What else? Shared library, number out of range, message too long, too many links. Oh, that's a useful one. Network is down, et cetera, right? So these are all very, very useful POSIX error codes that you can use if you're doing system level programming. We're not going to be doing our system level programming. Instead, we're stuck in what's called user land, right? That is our programs. You generally need to define your own error codes and use an enumerated type to do so. And that's what we'll do, all right? All right. Cool. Any questions on this? No? All right, so looking ahead here, next week we're going to start on arrays, and then after that I believe that we'll have some tooling that is debugging, after which then I think that we get into strings, but then we'll have our second exam. Before or after we start covering strings, but I can tell you that strings will not be on the second exam. The second exam will be everything that we've done so far since the first exam: functions, pointers, pass by reference, pass by value, arrays that we'll get into next week, and then debugging. And then we'll have another exam at some point. I forget what the date is, but it'll be the same format as the first exam. 24 hours to do it, and do it on your own. Otherwise, I don't want to start an arrays today, unless you want to. No? All right. No questions on error handling? All right. Then we'll go ahead and pick it up fresh on Monday with arrays.